This is a video key to the forces test given November 9th and 10th. This is for the version that had a sled on the last page. Another way to recognize it is there's no helicopter pictured on the first page, just the box is suspended from a ceiling. So in this case, we had to find the tension in each rope, and we're told that the lower box has a different mass, or we're given what that mass is. So when we sum all the forces, we don't write sigma F is equal to MA because it's true, it's just not very useful. So you have to have a free body diagram, and then your net force statement is based on your free body diagram. So in our system, I've combined the boxes so that the masses are treated as one. Because T1 doesn't really have any eyes or know how many boxes it's lifting, T1 just has to support the weight of all the mass that is beneath it. So the masses of the system are combined here. So tension 1 up and the weight of the system down is how we solve this problem in your notes. Same thing here. So in the net force statement, we list the vectors that we have drawn in our diagram, and we give them opposite signs when they're in opposite directions like this. Another way to start, instead of drawing the sigma, is to start with mass times acceleration. And then again, you need to list the vectors. Either way you start, you're listing as vectors. This is what we mean by specific. You must write specific net force equations. That's because that's the way to get it right. If you do something like this, which was actually kind of common, it's a little crazy because you're forgetting the mass is being pulled on by planet Earth. Weight really matters. So you need to list everything, and the best way to do that is by drawing it first. So in this particular form, there was a 10 kilogram box and a 20 kilogram box. So that's why I have 30 kilograms here. And I've just factored out the m and added the two accelerations together. So 9.8 for gravitational acceleration and 2 because it's given in the problem as that this is elevators accelerating upward. Upward means positive 2. So tension 1 is 354 newtons. Now, I have to now draw a second free body diagram. Have to, not optional. So when I draw the second free body diagram, this is just for M2. So M2 is being lifted by T2, so I named that M2, and it's got its own weight pulling it back down. So again, I write a new net force statement. One object only is in a free body diagram. So here you can see I've drawn only one, even though I've combined two masses. So each one is for one object. That means that's the only object in the net force statement also. So that means when you substitute the mass, it's just for this object shown in your diagram. Okay? So when you solve for it, for this particular form, 236 newtons was T2. There was a different version of that. This is still a test with no helicopter on the front and with a sled on the back. But in this example, the two boxes were the same size. Same technique gives you a T1 of 236 and a T2 of 118 newtons. How were the points distributed? Every free body diagram and every net force statement was worth 2 points. Now this is 2 points out of 50. So if you want to think of it as a percentage, it's 4 percentage points for the free body diagram here, and the net force statement here, and the free body diagram here, and the net force statement here. Correct answer for T1, correct answer for T2. Those are worth 2 points apiece. So this is 2, 4, 6, 8, 10, 12. And then I also gave another point for showing good substitutions. Moving on to the second problem, we had normal contact forces because two boxes remain in contact while one of them is pushed. So when that one of them is pushed, it pushes on the other box. And so the pushing that's going on right here is what we mean by finding that contact force, the normal contact force. We begin though by finding the acceleration of the boxes. So notice I've drawn a single box here with kind of an odd shape. That's because my free body diagram is allowed to have only one object in it. So in this case, I have no normal contact forces because there's one mass. So applied force forward, that's the push. You could have called it P for push. Little f backwards for friction. None of these should be called just plain F because everything shown is a force. You need a more specific label. Don't start off sigma F is equal to MA. It's not useful enough. Instead, list the vectors that you have in your drawing. You can see vertically I'm saying F is equal to MA, right? So you could also have just started off with mass times acceleration. S there stands for system. So right here I'm going to put in the friction. And now I'm going to substitute in the mass that I've been given by adding the two together. So this particular form had a 10 kilogram box and a 25 kilogram box. There was a different form where the push and the second mass was different. So once I put those in, I used the coefficient of friction that was given in the problem, the combined mass of the system, there's G for determining what's happening with friction, because it's mu mg, and there's the applied force of 90 newtons, and that gives us this acceleration. So I've now completed part A. In order to find the normal contact force, I have to make a separate free body diagram for a single mass only. Now, if this is for M2, I can see that the force of 1 is pushing on 2. That's what we're trying to solve for. The normal is different, the weight is different, because this is only mass 2. So when I sum these forces with a specific net force statement once again, okay, and I solve, I need to put in the acceleration that I just calculated from over here. So I want my best unrounded number for that. And now the only thing that's unknown is the force of the first box pushing on the second, and that allows me to solve for it. It is possible that you chose to draw a different second free body diagram. This is what the first one, that is the mass that's being touched by the applied force, looks like. Because this first one pushes on the second one pushes back on the first one. So here we have force 2 on 1. So you could have drawn either this one or this one. You did not need to draw both, even though you were asked to find part C, the other contact force. All you had to do was write this answer a second time, labeling it as part C. Why is there no work needed here? Because you're supposed to know by Newton's third law of motion, C must equal B. These two have to be the same. When object 1 pushes on object 2 pushes on object 1 with a force that is equal in magnitude. So this was my way of getting at, did you know Newton's third law? And if you knew it, you didn't have to waste any time doing any calculations for part C. So again, 2 points here, 2 points here, 2 points here, 2 points here. That's 8 points right there out of 13 for just the net force statements in the free body diagrams. Don't skip those. I've been telling you for many, many weeks. Those are worth a huge part of the credit. And then 2 points here for the correct answer, 2 points here for the correct answer, 1 point for having a C that matched B. So even if you got B wrong, you could get that point if you knew that C had to match B. Okay? On the other slightly different version of the test, there was a push of 70 newtons, and the mass of box 2 was different. So this is the acceleration, and this is the contact force. And again, of course, C and B must be equal to each other. The third problem was dragging a box by a rope. So you make a free body diagram. This time you need only one because we have only one mass. So the pull is up and to the left, just as shown in the picture. That means the X and Y components are to the left of the object. Now, in this situation, the normal does not equal the weight. It's really important that you know that because eventually you're going to be working with friction. The reason the normal doesn't equal the weight is there's a force at an angle. That's a dead giveaway. Another way to look at it is you have multiple forces in the up direction because that component right there, that's called PY. The vertical component of the pull is lifting, accidentally lifting the box. And so these two ups together work to balance the weight force. So when I sum the forces in the Y direction, the normal force and the Y component of the pulling force are both positive. The weight force is down and negative. So that pulling force is going to be P sine theta. And the pull was given to you when your pull is 80 newtons on this particular version. So you can just solve for the normal force. Now you know the normal force, which you'll need when you work with friction. So to figure out friction, in this case the coefficient of friction, I need to look at the X direction. So I'm now looking here where I can see the X component of the pull is parallel to the frictional force, but in the opposite direction. Because the pull is going left, the friction goes right. And I'm going to follow my habit of making friction negative because it's really smart if I choose the direction of motion to be positive. Because that way this sign and this sign will both be positive, and they need to do that. Okay, so when I solve for this, I've got everything I need to know to find the force of friction, but that's not what the problem asked for. So you may at this point substitute in mu times the normal force right here, or you could do it as a separate calculation here. So mu is equal to the force of friction, there we go, calculated from the X component directions, the X direction, divided by the normal force, calculated from the Y direction. You want your best unrounded number, and that is the correct answer. On the other version, we had some slightly different numbers on that box dragging. It was still an 18 kilogram box at 36 degrees, but the acceleration of the box was different and the pull was different, giving us a normal force of 123 newtons, a frictional force of 43.29 newtons. Remember, you don't have to calculate the frictional force. That's why it's not boxed. What you needed was the coefficient of friction, which is about 0.35. Continuing on to the last problem on the free response test. Here's the sled that I was talking about at the beginning, is how I tell apart the tests. The other classes, or the other people who I should say, who took a different version, had a problem with the truck on the last page. And by the way, the multiple choice that you had coordinated with this. So if you did not have an inclined plane on the multiple choice, you had it here. If you did not have a truck problem on your free response, you had it on your multiple choice. Okay, so I'm given all this good information, and I have magic words up here. Constant velocity, that's great. That tells me right away acceleration is 0. That means the original velocity is 2.3, the final velocity is 2.3, and the average velocity is 2.3. So easy peasy, I don't have to worry about any acceleration equations. So velocity is distance over time or displacement over time. So just do the finger flip to solve for time. Put the numbers in you're given, and you've got your velocity in seconds. You've got your time in seconds. Excuse me, getting tired here. Here is the box I was shown. It's at that angle. It matches the picture at that angle, so my box should be at that angle. Because the normal force has to be perpendicular to it, friction has to be up the slope, and W has to be straight down to the center of the earth. If you got all three of those right, that was worth 2 points. I'll mention points up above. This answer was worth 2 points, showing the substitution was worth 1 point, and showing the algebraic formula is worth 1 point. Never miss those easy points. Go ahead and show those easy things. Okay, down here you had to find the frictional force, not the coefficient, so don't use mu at all. In this case, when you sum the forces parallel to the ramp, there is a hidden component I haven't drawn right here. This one right here that's W parallel that's going down the ramp. As you can see, I should have labeled my weight on the downhill side. You've heard me say that often enough. So if I label my weight on the downhill side, it's a little bit easier for us to see that W parallel is coming in this way. So when I sum the forces parallel to the ramp, I have 2. Friction up the ramp, W parallel down the ramp. So you got 2 points for a net force statement that lists specific forces. It doesn't matter if you make friction positive or negative. Because you're solving for it, you can leave it without a sign, and the math will tell us the sign at the end. But it also doesn't matter because the problem said calculate the magnitude of friction. So that means you're going to report an absolute value anyway. So don't worry about it. Okay, you got a point for recognizing that you know how to calculate, or showing you know how to calculate W parallel by using the sine of the angle. Because in this component triangle that's underneath, there's theta right there. Now, why didn't I start off drawing those components? Because the problem very clearly said only draw the forces, not any components. So if I actually did this, what I'm doing right now on the AP exam, I wouldn't get any points at all, because they would take off a point because I drew W parallel, and they would take off a point because I drew W perpendicular, and that would obliterate the plus 2 points that I had earned for having the other force vectors correct. I did not do that to you. I should have, but I didn't. So please watch those instructions in future. Okay, so summing the forces parallel to the incline lets us solve for friction, and it helps tremendously to recognize those magic words. This is sliding at constant speed. That means acceleration is 0. That means the force of friction is equal to the force of W parallel, at least in magnitude. And so we can just go ahead and substitute in the mass given, 9.8, and the sine of the angle that was given to get that frictional force. If you had a different version, you saw 2.6 meters per second, a different speed, and a different distance down the slope. So the answer for time was 6.54. The free body diagram is exactly the same. The answer for friction is 61.3. So this was an 11-point problem. So that concludes the free response portion of the forces test. You can hang on to this, remember, to study from, and I hope you will. Bye.